Hey guys, so today I'm going to be going over how to actually design a synchronous counter, because I've been seeing a lot of ripple counters and there's really no reason to build a ripple counter, because for every bit you add to your counter, the clock cycle has to increase to compensate for the extra delay through the ripple. So we're going to build a synchronous counter which has one gate delay per T flip-flop, or per whatever flip-flop you decide to use. And since it's one gate delay per flip-flop, it's synchronous across all of them instead of increasing gate delays if you were to ripple through. So let's go ahead and grab a T flip-flop. So we can go to our components. This is digital, by the way. I will give a link to download it into the description. So if we go to our flip-flops here and we grab a T flip-flop, I'm going to explain how their model of the T flip-flop works. It's pretty easy. We're going to grab a component IO, we're going to grab an output pin, and we're going to put it there. We're going to grab some I/O again, and we're going to grab two input pins, and how I'm going to do this, I'm just going to Control C and Control V one. So we'll wire up the clock. Whoops. And wire up the toggle enable. Okay, so if I run this, if I pulse the clock, nothing is happening on the output. If I enable the toggle and clock it, it toggles. So this has a built-in enable in the model that we can use, or if we didn't want the enable, we could do that, and you can see it gets rid of the toggle line and just gives you the clock. But we want the enable. Okay, so what we're going to do now is, on the first one, we want it to toggle every time. So on the first one, we actually don't need to enable the toggle or disable the toggle. We want it to toggle every time there's a clock pulse. So now you'll see that if I delete this and we play this, every time, because it's being told to toggle and the clock edge is there, it toggles. So the model is able to work like that. Okay. So we have a 1-bit counter, great. But now we want the next bit above to toggle on the clock and toggle when this one is off. So the way we actually want to achieve that is, well, we actually want to toggle every other time up here. So this toggles every time, this next one above it toggles every other time, the one above that every other fourth time. So we're basically dividing the signal in two. So what we want to do is we're going to grab the inverted output and we're going to bring it up like this. We're also going to bring our clock and bring it up like this. So the next bit here, we're just going to steal like this. We'll bring it up a little bit here. So the next bit, we're going to need a component, we're going to need logic, and we're going to need a NOR gate. I'm going to right click on it, go to advanced, make it small like that. And then for this one, we just need two inputs, so we'll leave it like that. We're going to move this down so we can actually fit that gate here, and this is going to go on the toggle enable. So the toggle enable is going to say, when this output is true, and the clock is true, the other thing we want to do is tie the clock to all of them. Like that. Okay. So now we'll copy this. We'll put this up on the Q output like that. And now we'll see what happens. So we clock it, clocks once. The Q naught is now off here. So if this one gets toggled or that one gets toggled, we'll see that it moves. Nice. Now since this one is on, this is going to get clocked and while this turns low, and that'll stay on. And now we do it again, and it rolls over. And there was synchronous. There was no delay because we have one clock delay here, but oh wait, there's no clock delay here. So what we need to do to actually make this synchronous, I'm going to go like this, and I'm just going to go to components, logic, is there a buffer? I'll just use an OR gate. The OR gate would presumably have the same delay as the NOR gate. And I will tie those together like that. So now we have a gate delay here. We have a gate delay here. Okay. So now if we wanted to add another bit, how would we do it? Well, we'd take the T flip-flop, we'd paste another version of it up here. And now what we're going to need is the Q bar output here. We'll bring this up. We'll bring this up. Bring that up. Like that. Okay, so now we know that the clock needs to be tied in here. And now for the toggle, we're going to need one of these NOR gates. I'm actually going to move this over like that to toggle, but now we need 3 inputs on this because now we have this, that, and the one behind it that we need to hook up. So we could put in 3 inputs, and now you'll see we take the not Q of the last bit, and of the previous bit, and of the clock. And so when this clock happens, we also need to tell it to actually clock this. So we only want to toggle when the clock is there, and we only want to toggle when the previous bits tell it to. And of course we need to tell it to clock all the times as well. So this is enable and clock goes in like that. That's why for this model it needs to be done like that. And so now if we copy another output bit to this, you'll now see that we start at zeros. I clock this. This first one generates, which tells the next one that when this goes low and then high again, it will toggle. So it went low, toggle enable is true, and now when we clock it, boom, it goes over. Now we can see the toggle enable is true on this one, but now it's not anymore. But now next time we clock it, this one toggles every time. So nice. Now we want this to roll over synchronously, so both of these should turn off at the same time as that turning on. Now you can see the toggle enable is turned on, so that when it gets a clock edge, it will turn on. And you can see that this toggle enable will be turned off when this clock line goes high at the same time it gets the clock. So clock line goes high here while it gets the clock, so it's set to zeros. While this one, the clock line went high and the clock line was there, so that actually turned it off and had it to toggle. So this is how you get a synchronous counter. And you can do this in Minecraft using one of those diode lines, like a slab tower. Because a slab tower has forward propagating NOR gates. Whereas with this, we had to run a wire for each one. And, you know, so here we can add another bit, just for shits and giggles if you wanted. So, Control C, Control V, move this over, Control C, Control V, make this 4 inputs, and it really is as simple now as bringing this one up, and then hooking up all the previous bits. That's why I brought those wires up like that. Then we need the clock line, and then we tie the clock in here, and like that, and boom. And now we can clock through it. Yep. So there's your synchronous counter. The other way you can do it is you can go to Components, Memory, Counter, or Counter with Preset. And then here you go, you have a data in right here, or data, direction in. Okay, so this can count up or down. The in, the word is stored on the counter when the LED is set. So if load is on, then the word in here will get set in there. This is multiple bit input is the input here. Clear, so you can set the zeros. So there's an overflow and an output. So if you were to chain counters together and you wanted the next one to toggle the clock, you could have the overflow toggle the clock, the one above it, and there's an enable for this counter. Or the overflow could be the enable pin for the next counter, and then the clock could be able to clock it at the same time. However you wanted to do it. But yeah, this is also a synchronous counter, and you can make that however many bits you want it. So if you want 16 bits here, you wouldn't have to sit here and build a carry table where eventually the last NOR gate would have 16 inputs. This just has the carry logic built in. Also, if you were to export this as an FPGA code, the counter here will be faster by using the built-in ++ increment symbol, which uses the carry look-ahead cells in your FPGA. Whereas if you were to build it like this, you're going to have gate delays through the logic elements. So like the FPGAs have certain cells for like carry look ahead logic, and they have certain cells for just doing general purpose logic. And obviously, if you're doing carry look ahead in the general purpose cells, it's going to be slower than doing carry look ahead in the carry look ahead cells. So if you were to use the built-in logic symbol like this, when it gets exported to VHDL code, it becomes an I++ kind of incrementer, and it knows how to handle that, versus if you were to do this, it just becomes like, you know, a state machine, which is going to be slower than using the built-in logic for that state machine. That's all I wanted to say, but if you wanted to know the logic behind making a synchronous counter, you could see here now, 1 gate delay, 1 gate delay, 1 gate delay, 1 gate delay, but each time they get more and more inputs, so it's going to grow pretty big. And that's also why I kind of offset them like this so you can get the wires up, because doing them all flat would be a pain in the butt. So yeah, that's it, and I hope you guys understand, and thanks for watching, and I will see you guys next time.